Hello, my name is Nathan Green, an electrical engineering graduate student working with the Alaska Center for Energy and Power. I'm here to talk about designing a microgrid which is primarily powered from a low-temperature geothermal heat source and an organic Rankine cycle generator. I will discuss some background information about microgrids and some challenges in implementing them, both in general as well as specific to ORCs. Then, I'll go on to discuss how we intend to address those challenges at the Alaska Center for Energy and Power. The Alaska Center for Energy and Power has been looking into geothermal options around Alaska for a while now. Recently, that effort has expanded as one component of a grant from the Office of Naval Research. To get started, I want to discuss some of the sites we've been looking at. The Pilgrim Hot Springs are about 60 miles north of Nome. You can see Pilgrim here on this heat map. The resource is fairly comparable to Chena Hot Springs over here, near Fairbanks. The Pilgrim area is owned by Unatak LLC, a consortium of native corporations and other local groups. For the past several years, they've been working with the Alaska Center for Energy and Power to develop the hot water resource. Prior to this, there was no modern infrastructure, only a few abandoned historic buildings. In the last few years, a wellhead has been installed along with a small sitting pool. Currently, a greenhouse is being built. If affordable power can be extracted from the heat, then winter grow lights can be installed and fresh produce could be grown year-round. The images on the right are neat examples of heat flow. On the top, a thermal camera image of a creek is overlaid on top of a normal photo. Notice how much warmer the water is compared to the banks. On the bottom, you can see steam rising off the creek in the morning. In addition to Alaskan sites, we are also looking internationally. Iceland has extensive experience utilizing their geothermal resources, which makes sense considering it is a volcanic island. But most of that experience is with large-scale, high-temperature electrical generation. The high-temperature geothermal areas are highlighted by red dots on this map. Their lower temperature resources, marked by black dots, are used for district heating loops, but not electricity. Despite this, there are some opportunities for lower temperature sites that have yet to be realized. The pumps for all the district heating loops are electrically driven, but electricity in some rural areas is less reliable than the heating system needs to be. To address this, they currently use diesel generators to run the pumps when the power is out. But if this could be done with ORCs instead, then the residents would not need to rely on diesel to stay warm if the larger grid goes out. And diesel is even more expensive there than it is here. While each individual low-temperature site may not have a lot of available power, they can add up, and you can see just how many there are. The overarching goal of this project is to be able to determine whether or not it is viable to install an ORC as a primary power source for these or similar sites. To do that, we will develop a combined thermal and electric energy balance model for an ORC generator and microgrid using MATLAB. The model will tell us how much energy we could expect to get out for a given set of inputs, as well as how much energy we could expect to lose along the way through various inefficiencies. Next, the model would need to be validated. This can be done in the Power Systems Integration Lab run by the Alaska Center for Energy and Power. Once the model is validated, we can go back and look at the expected results for Pilgrim or the Iceland heat loops and estimate costs. Ideally, this model could even be expanded to include other energy resources, such as hydrokinetics, to quickly estimate whether it is worthwhile to develop the resource. Next, I want to give a bit of background on the Rankine cycle and the machines that use it. Basically, A working fluid starts at point 1 in this image and is pumped to a high pressure level. At point 2, heat is then added to the fluid, causing it to boil or vaporize. It doesn't really matter where the heat comes from. In the cases we're looking at, it comes from geothermal hot springs, but coal-fired and nuclear plants generally use Rankine cycles as well. Next, from point 3, the evaporated, pressurized fluid flows through a turbine or expander, spinning a shaft of a generator. This converts the mechanical power to electrical. After flowing through the expander and reaching point 4, the fluid pressure drops back to the original level, but it remains a hot vapor, but not quite as hot as before. The fluid then flows through a condenser, which extracts the heat that wasn't able to be converted into work and brings the fluid back to its original liquid state, where the cycle starts anew. Now, in practice, there are often additional stages involving preheating and heat recovery in order to improve efficiency of the process, but this is the gist of it. In theory, you could use most any liquid as the working fluid in a Rankine cycle. The key is finding the appropriate fluid for the expected temperature and pressure ranges. Water is often used as a working fluid for coal and nuclear plants, as well as high-temperature geothermal sites. It's cheap, readily available, and if there's a leak, well, it's a fairly innocuous fluid. But the major factor is the vaporization curve. For high temperatures, no extraordinarily high or low pressures are needed to vaporize or condense water. However, for low temperatures below 100 degrees C, water doesn't quite work. Organic fluids, such as refrigerants, work much better at low temperatures. You can see in this graph a comparison of the vaporization curves of a common ORC working fluid and water. The curve shows what the pressure is needed for a given temperature to allow the fluid to vaporize or condense. At a pressure around 1 atmosphere, this fluid vaporizes at around room temperature, while water vaporizes at 100 C. While these organic working fluids make the process possible at low temperatures, there are still some issues. The lower temperature means there is less energy available per unit volume. This means the power needed to pressurize the working fluid makes up a larger portion of the power you get out. If the temperature gets too low, it may just barely be able to keep itself going with no power for anything else, no matter what fluid is used. The model will help us find that level and tell us how much power we have to spare. Now, I'd like to give a little bit more detail into microgrids and what they need. By definition, they are geographically localized electrical networks. Usually, they are connected to a larger grid, but are able to disconnect and operate on their own. A good example of a microgrid is the UAF campus. The 11 megawatt power plant can power the campus, but depending on current costs, some or all of the electrical power will come from GVEA and the larger grid. Many Alaskan villages are considered permanently islanded microgrids because they don't have a larger grid to fall back on. This image here is of a hypothetical Alaskan village with examples of different key components of a microgrid. Microgrids will always have sources of power generation as well as loads which utilize the power. In an effort to improve their reliability or increase their independence from the larger grid, many microgrids also take advantage of some form of energy storage. And finally, since the power utilized or generated among sources, storage, and loads may not be compatible with each other, there is likely some form of electrical conversion along the way, though not shown directly in this image. Sources are fairly straightforward. They generate the electrical power used by the loads. Diesel generators are popular in Alaska because they are very versatile and robust at the sizes needed. Hydroelectric turbines use a reservoir or penstock to get water to drop in a fairly controlled fashion. They are very dependent on local geography, but examples can be seen around the state. These two sources are examples of firm generation that usually form the backbone of a microgrid. Solar photovoltaic panels have only seen modest implementation here because of the long winters, but as they come down in price, the spring and summer production can make them worthwhile. Wind turbines have seen a bit more implementation in Alaska than solar. The cold, dense air is generally a plus. Solar and wind are both intermittent resources, meaning we have very little control over how much power is produced and when. Hydrokinetic turbines use run-of-the-river instead of a reservoir or penstock like traditional hydro. So far, there have only been test installations, nothing permanent. China Hot Springs are already running ORCs on some of the lowest geothermal resource to date. Hopefully, Pilgrim will follow. Both of these resources can, in theory, be used to form a grid because they are more predictable and their changes are slow-going over the course of a season. However, there are no examples so far of this being the case. Loads are the ultimate reason for larger grids and microgrids alike. They are our lights, microwaves, washing machines, whatever. Since microgrids are smaller, they are generally less robust than larger grids in the event of a big change in load. To help minimize the effects of these load changes, it can be helpful to prioritize loads into those that are firm and those that are dispatchable. Firm loads need the energy immediately, like lights or a toaster, while dispatchable loads may need the energy over the course of the day, but timing is flexible, like a refrigerator. In general, treating every load as firm is simpler because dispatchable loads need additional controls and infrastructure for them to know when it is appropriate to turn on and off. But it could be worthwhile if it gives some relief to a heavily taxed grid or allows intermittent resources such as wind or solar to be optimally used. Storage can provide a similar function to a dispatchable load, but is even more flexible. It can act as either a source or a load depending on the microgrid design as well as the current conditions. Flywheels and battery banks are shown on this example, but other types of storage systems include supercapacitors, pumped hydro, and more. In general, the choice of storage depends on how long you intend to store the energy and how quickly you want to release it when using it. As mentioned before, the form of electricity a load uses isn't always the same as what's produced, so power electronic conversion is used. Rectifiers convert AC to DC, inverters convert DC to AC, variable frequency drives convert AC from one frequency to another, and finally, DC to DC converters will increase or decrease the voltage level. Each of these different conversion devices uses some form of electronic switching to control the flow of current such that the desired output is obtained. Depending on the application, some converters may be unidirectional, like going from a DC solar panel to a DC battery, while others may be bidirectional, like a converter that can either charge a battery from the grid or supply power from the battery to the grid. In addition to the components of a microgrid I've discussed, there are several other very important characteristics that must be accounted for. Loads are rated and generally expect to operate at a certain voltage and frequency. The grid-forming source that provides the backbone of a microgrid must be able to maintain and regulate these values, otherwise some loads may be damaged. Typically, a diesel generator, hydroelectric turbine, or high-temperature Rankine cycle generator will form and regulate the grid, although certain types of grid-forming inverters are capable of doing so as well. Grid stability is very tricky in microgrids because what would be a very small change in a normal grid is much larger in a microgrid, relatively speaking. The changes in load can affect the voltage or frequency levels. Rotational inertia of a spinning machine can help mitigate the effects of load changes, as the large mass can just roll through the variations. Electrical faults are never wanted, but they happen, so the infrastructure must be able to deal with them as safely and as reasonably as possible. The sources should be able to supply enough current to burn up the tree branch that fell on the lines, or at least enough to trip the breakers to minimize damage to the rest of the system. Lastly, the spinning reserve of a grid represents the capability of adding additional load to the system at a moment's notice. When the Super Bowl ends and everybody flushes their toilets all at the same time, their water pumps will kick on at the same time too, and something needs to be able to deal with that extra load. Similarly, if intermittent resources like wind and solar are connected to the system, then something needs to be able to pick up the load if the wind stops or a cloud moves in front of the sun. Traditionally, spinning reserve is made up of generators on the grid not being run at full capacity, so they have room to spare. These days, storage, such as the Battery Energy Storage System, or BESS, here in Fairbanks, can also provide spinning reserve. Now that I've covered some background on ORCs and microgrids, I'd like to give you a general overview of the model and its pieces. The model will take as inputs a resource profile of the heat source and heat sink, as well as a load profile consisting of expected loads and their durations. Additionally, each device in the model will have several physical parameter inputs to make the necessary calculations. Along the way, from source to load, the model determines the power input and output for each component. The losses are summed and the total efficiency is calculated. Or maybe there isn't even enough power at the source to power everything. Either way, the results are returned and we can evaluate viability. Currently, I have the ORC portion to model the heat flow and an induction generator model that links the ORC component with the electrical portions of the model. Next, I will work on a grid-forming inverter, a load profile, and a shell to tie everything together. Having a computer model is all well and good, but without verification, it's hard to say just how accurate it is. Fortunately, the Alaska Center for Energy and Power operates a microgrid testbed at its Power Systems Integration Lab. The lab can operate as if it were a small Alaskan village with a number of different sources and loads. This is a list of some of the equipment on the testbed. One particular piece of equipment of interest is the wind turbine simulator. A motor can spin an induction generator at various speeds corresponding to a hypothetical wind blowing at different speeds. We could instead spin the generator to correspond with different hypothetical temperatures to act as an organic Rankine cycle generator. However, that is not enough on its own. Induction generators, which many commercial ORCs use, cannot form a grid. We would need to combine it with the grid-forming inverter and battery bank in order to power the load banks without running the diesel generator. Once the model is validated, we can run a wider range of simulations using the MATLAB model, which is faster and more affordable. So, to bring this all together, there are a lot of low-temperature geothermal areas, both here and abroad. Unfortunately, it's not very obvious whether or not any particular site can viably be used to generate electrical power. Not only that, but if there is not already reliable power nearby, then you need a way to form a local microgrid. Once completed and validated, The model we're developing should give us a tool to quickly assess what a geothermal site is capable of producing. In the future, I hope this model can be expanded to include other resources such as hydrokinetics, tidal or wave power, and more. Thank you all for listening. Does anybody have any questions?